Have you ever stopped to think about what a simple glass of lemonade and the coolant in your car engine have in common? I mean, they seem like they're from totally different worlds, right? But here's the thing, they're both run by the exact same fundamental rules of chemistry. Today, we're going to dive into the science of solutions. And trust me, the universal laws that govern how things mix are way more powerful and frankly more surprising than you probably think.
So let's start with a really simple question. Picture this. You make a glass of lemonade, you give it a really good stir, and you take a sip. Then you finish the whole glass. Was that very last sip any sweeter than the first one? Well, if you did a good job stirring, the answer is no, of course not. And that simple, everyday observation, that's our perfect doorway into understanding what chemists call a true solution. So what is it that really makes that perfectly mixed lemonade different from, say, trying to mix oil and water? Well, it all comes down to what's happening at a molecular level, completely invisible to us. And to really get it, we need to start speaking the language of chemistry.
Okay, so that lemonade we made, that's a textbook example of a homogeneous mixture. Just like salt dissolved in water, its composition is perfectly, completely uniform all the way through. You can't look in and see the little sugar crystals, right? Everything just exists in one single consistent phase. Now, the total opposite of that is a heterogeneous mixture. Think sand and water. You can clearly see the different parts, and they exist in their own separate, distinct phases.
But a true solution is a very specific kind of homogeneous mixture, and what makes it special all comes down to scale. The stuff that gets dissolved, we call that the solute, the particles are less than 1 nanometer big. That is so mind-blowingly tiny that you can't see them even with the most powerful microscopes on Earth. They're never going to settle out at the bottom. They are perfectly and permanently mixed. Now, if we really want to study solutions, we have to get precise. Just saying a solution is strong or weak, that doesn't really cut it for a chemist. We need a way to measure exactly how much solute is dissolved in the solvent. And this brings us to the language of concentration. First up, we've got molarity, which we write with a big M. It's probably one of the most common ways to measure this stuff. It basically asks how many moles of our solute are packed into 1 liter of the entire solution. Now, mole might sound a little weird, but it's just a word chemists use for counting particles. Kind of like how a dozen means 12. A mole is just a chemist's dozen, a really, really, really big dozen. So molarity is all about the amount of stuff per total volume. Next is its close cousin, molality, with a lowercase m. Now, the difference here is subtle, but it's super important. Molality measures the moles of solute per kilogram of just the solvent, not the whole solution. And this is key, because think about it. The mass of something doesn't change when you heat it up, but its volume can. That makes molality the absolute go-to when you're doing experiments where the temperature might change. Okay, to make things a little easier as we go, let's look at the shorthand that chemists use. Think of this as our little cheat sheet for solutions. A is always the solvent, B is the solute, W stands for mass, a capital M is for molar mass, and N is for that number of moles we just talked about. This is going to be super helpful in just a minute. And finally, we have the mole fraction. Imagine you could just freeze time and count every single particle in that solution, all the solute particles, all the solvent particles, everything. The mole fraction just asks a simple question. Out of all those particles, what fraction of them are the solute? It's just a pure ratio, so it doesn't have any units, and if you add up the mole fractions of everything in there, it will always equal exactly 1.
All right, enough theory. It's great, but let's put it to work. We're going to solve a little chemical mystery that shows you just how powerful these concentration formulas really are.
So here's this scenario. A chemist finds a bottle with no label on it. They carefully measure out exactly 5 grams of this unknown white powder. They dissolve it in water until they have exactly half a liter of solution, and then they measure its concentration. Turns out it's 0.25 molar. So the question is, can we figure out what that mystery substance is with just that information? And the answer is absolutely, yes, we can. And the process is actually pretty slick. We start with our molarity formula. We already know the molarity and the volume, which means we can easily figure out the number of moles of the stuff. And since we also know that moles are just mass divided by molarity mass, we can just rearrange that formula to solve for the one thing we're missing, the molar mass of our mystery powder. And when we plug in the numbers, 0.25 molar, 5 grams, and half a liter, the math spits out a molar mass of 40 grams per mole. A quick look at a periodic table tells us exactly what we've got: sodium hydroxide, NaOH. And just like that, mystery solved, all thanks to the precise language of concentration.
Now, being able to identify a substance is pretty cool, but that's just scratching the surface. The real magic of concentration is understanding how it predictably changes the physical properties of the liquid itself. It turns out that when you dissolve something, the solution gets these 4 predictable, really fascinating, and incredibly useful new behaviors. They're like a solution's 4 hidden secrets. These secrets are called colligative properties, and here is the absolute golden rule, the most important thing to remember. These properties do not care what you dissolve, they only care how much you dissolve. It's all about the quantity of the solute particles, not their quality. The number of particles is the only thing that matters.
And here they are, the big 4. Each one of these is totally fascinating, and they explain everything from how we de-ice roads to how our own kidneys work. But for today, we're going to focus on the first 2, because they're a powerful duo that acts like a perfect chain reaction, the lowering of vapor pressure, and how that directly causes the boiling point to go up.
So let's really explore this chain reaction. It all starts the second you dissolve something. First, the pressure from the liquid's vapor goes down, and then, as a direct result of that drop, the temperature you need to get that liquid to boil goes up. Let's break down exactly why. Okay, imagine a glass of pure water. Right at the surface, water molecules are constantly just leaping off, turning into a gas or a vapor. This cloud of escaping vapor creates a pressure right above the liquid, and we call that vapor pressure. In a pure solvent, it's like an open highway for those molecules to escape. But now, let's dissolve something like sugar in that water. Sugar molecules don't really evaporate, but they do spread out everywhere, and that includes right at the surface. And up there, they act like little roadblocks, just physically getting in the way, making it harder for the water molecules to find a clear path to escape. It's like trying to exit a building through a really crowded doorway. Fewer people can get out at once. And this effect isn't random at all. It's perfectly predictable. There's a principle called Raoult's law that puts it into a nice formula, but the main takeaway is really simple. The more the vapor pressure drops, the more solute particles you've added. The more roadblocks you put in the way, the lower the vapor pressure goes. It's a beautiful, direct relationship. So we've established the vapor pressure is now lower. So what? Well, what happens next is a huge deal, because this directly and unavoidably changes another physical property, the boiling point. Let's connect the dots. First, we need to be crystal clear about what boiling actually is. It's not just about getting really hot. A liquid boils at the very specific temperature where its own internal vapor pressure gets strong enough to match the external atmospheric pressure that's pushing down on it. That's the magic moment when bubbles of vapor can finally form and escape. Okay, now think about what this means for our solution. We already know it has a lower starting vapor pressure because of all those solute roadblocks at the surface. But to make it boil, it still has to reach that same finish line, that same atmospheric pressure. It has to make up for that deficit, and the only way to do that is to pump in more energy, more heat, to get that lowered pressure all the way up. The result? A higher boiling point. And just like with vapor pressure, this effect is something we can calculate. The formula shows that the change in the boiling point, what chemists call delta TB, is directly proportional to the molality of our solution. That little kb is just a constant that's unique to whatever solvent you're using, but the bottom line is simple. The more concentrated your solution, the bigger the jump in its boiling point.
And this has real-world effects you've probably used a million times. When you add salt to your pasta water, you are literally raising its boiling point. That water might now boil at, say, 102 degrees Celsius instead of 100, and that hotter water actually cooks your pasta faster. And in labs, chemists use this exact same idea to check if a solvent is pure. If it doesn't boil at its precisely known temperature, they know it's got some impurities dissolved in it.
Okay, that was a lot of information, I know. So let's put that new knowledge on its feet with a few quick questions to see how these ideas play out in the real world. First question, we all call it antifreeze, right? But think about what we just learned. Adding that stuff, that solute, to the water in your car's radiator absolutely elevates the boiling point. So does it also help keep your engine from boiling over on a blistering hot summer day? Yes, it sure does. It's really an antifreeze and an anti-boil. All right, second question. Remember our definition of boiling? It happens when vapor pressure equals atmospheric pressure. Well, up on a high mountain, the atmospheric pressure is a lot lower. So do you need more heat or less heat to get the water's internal vapor pressure to match that lower external pressure? You need less.
Water on a mountain boils at a temperature below 100 degrees Celsius, which is exactly why it takes so much longer to cook things up there.
And for our last one, a bit of a trick question. Remember, colligative properties depend only on the number of dissolved particles. When 1 mole of sugar dissolves, it just stays as 1 mole of sugar molecules floating around. But when 1 mole of salt, NaCl, dissolves, it breaks apart into 2 moles of particles, 1 mole of sodium ions and 1 mole of chloride ions. So which one has more particles? The salt solution, by a factor of 2. And therefore, it's going to have the higher boiling point.
So the next time you stir sugar into your coffee or salt your pasta water, remember, you're not just cooking, you're running a little experiment with colligative properties. These invisible laws are always at play, quietly making the world work the way it does. And the real question is, after today, what other everyday things will you see a little bit differently now that you know the secrets of solutions?